Okay, I think we can start. So today we have a very interesting speaker, Maureen Cohen. She has a quite interesting CV, actually. She started out, well, first of all, you will hear that she's fluently in English, but her mother language is German, if I understood well. But she started out not in science, but in classics. So she did her bachelor in classics in the University of California. Then went on to obtain a master degree in archaeology of the Mediterranean area, if I remember well. And then she did some translation work also, so she's a fluent translation German-English. Then she completely switched interests, I guess. And she went to do mathematical physics. And then one thing led to the other, and now she's doing a PhD in exoplanet research at the University of Edinburgh. And we are happy to have her here to give a talk on the exoplanet atmospheres. Please.
Great, thank you for the introduction. Yeah, my name is Maureen. I'm at the end of my second year of my PhD at the University of Edinburgh, and I've been doing theoretical studies of exoplanets with a focus on atmospheric dynamics, and especially on variability caused in exoplanet atmospheres by the dynamics and how that might affect our observations. So the main focus of my work so far has been on waves, which are the source of most of the variability that we see in our simulations. And before I get started, I just want to emphasize that all the data in this presentation is simulated. So I'm not an observationalist, and I haven't yet worked with telescope data, but this is all modeling, essentially. So in our modeling, we use 3D general circulation models, and the one that we're using in particular is the Met Office Unified Model. This is a global climate model that the UK Met Office uses to forecast the weather and also to predict the climate in the long term. So it has both these capabilities. And it has been configured by a group at Exeter, the Exeter Exoplanet Theory Group, for several exoplanets, including both hot Jupiters and Earth-like planets, and I think they have some kind of sub-Neptune type configurations as well now. But my research has been primarily about Earth-like planets, and in particular, we've worked with simulations of 2 planets, so Proxima Centauri b, which is our closest exoplanet, 4 light years away, and Trappist 1e, which is in the Trappist 1 system 39 light years away. And for your astronomers, you probably know, but there are 7 Earth-like planets in the system. They're all transiting in front of the star. They're all rocky, and 3 of them are in the habitable zone. So essentially, we're using these Earth-like climate models depicted in the image to study Earth-like planets with a few small differences, mainly that they're orbiting M-dwarf stars and that they're tidally locked. So a little review of transit spectroscopy. How do we know things about exoplanets? How do we study exoplanet atmospheres? As shown in this GIF here, when an exoplanet crosses the disk of a star, when it passes in the line of sight between Earth and a star, it blocks out part of that light, and it blocks the light differentially. So it will block some wavelengths more than others. And we can plot that, so we can make it a spectrum where we have the light wavelength on the x-axis, and then the depth of that drop in percentage, or rather in ppm, on the y-axis, and that will tell us how much light is blocked at each wavelength. And from that, we can infer what kind of atmospheric chemistry this planet has. And a quite important aspect of this type of observation is that we're not observing the whole disk equally, but we're looking at the kind of atmospheric circumference, the planetary terminators, and that is relevant because our simulations show quite a lot of interesting activities in the terminator region. And so the simulated observations I have in this presentation are of data from around the planetary terminator. So that's a region of interest that we want to keep in mind. So the planets that we're simulating using our big our GCM, the the Unified Model, are habitable planets which are tidally locked. And the reason we model these planets is because we think they're likely to be detected. We think that most habitable planets that we will detect in the future are probably going to be tidally locked. And that's because the sort of most common type of star is are M-class stars, or like variations of M-class stars, because they are low-mass, cool stars, and they take a long time to burn out. And in order for a planet to be habitable, if it's orbiting an M-dwarf, it has to be very close in because these stars are cooler. And usually if they're that close in, the tidal forces on the planet are big enough that it will become tidally locked. And for the Earth-like planets that we're looking at, that takes quite some time, like on the order of a billion years. And for hot Jupiters, it's a lot faster. But because M dwarfs have such a long lifespan, we do expect that that's enough time for even Earth-like planets to become tidally locked. And what you're seeing in the simulation here is on the left-hand side, this is a map of the surface temperature of a tidally locked planet. And you can see that one side of the planet is quite hot, this side here, and then the other side is cooler, but it's not sort of undifferentiated. So there's an area around the equator which is somewhat warmer, and then there's these cold spots, which are kind of north and south of the equator, the coldest spots on the surface. And then on the right-hand side, you see an animated GIF of the wind streamlines on a tidally locked planet. This is at 5 kilometers, and it's just kind of going on a monthly basis. And this kind of just summarizes the basic general circulation of tidally locked planets. So the substellar point, the hot spot is right in the center here, and the cold spots are here where these vortices are. And you can see that there's a zonal jet along the equator, so there's a flow consistently in this direction. And then here in the center, there's a rising bubble of air where the air is warmest, and on the night side, that air subsides. So there's an asymmetry in the vertical wind. And then you can see these kind of rotating areas of air, the night side vortices, which have quite a large impact on the circulation and potentially on our observations. So this is a really nice image from this paper in the corner by a group working at University of Exeter, who decomposed the general circulation of tidally locked planets in simulations in order to better describe what's actually happening in the fluid dynamics. And I've included this because it will be relevant for my findings later on. But essentially, there are 3 components of this flow. So the red, the zonal jet, which is this equatorial stream, which is just flowing around the planet, it redistributes a lot of heat to the night side. Then the blue, what they call the overturning circulation. This is the sort of hot air bubble that's rising on the day side and then cold air subsiding on the night side. And then the green are these kind of rotating vortices, which we saw on the GIF on the previous slide. And these are what's known as planetary scale waves, or Rossby waves, which are these sort of large-scale patterns of rotating air, which are also found on Earth. But they take on a unique pattern in our simulations of tidally locked atmospheres. Okay, so that's kind of the background and the motivation for our studies. And I'll be talking about 2 projects that we've worked on involving variability on tidally locked planets. And so kind of the basic fact that we're starting with is that tidally locked planets, even though we simulate them without any kind of periodicity in their orbital configuration, so they don't have days because they're not rotating relative to the planet. They don't have seasons because we simulate them without obliquity or eccentricity. They don't have years, again, because they're tidally locked, but they still have these periodic phenomena, and that happens because of atmospheric waves. So it's kind of a purely geophysical fluid dynamics phenomena in our simulation, but it actually has very large impacts on the climate and potentially on our observations. So the first project I'll talk about is examining a stratospheric wind and water vapor oscillation, which is analogous to the quasi-biennial oscillation on Earth, and I'll talk a little bit about what that is. And then the second project is about variability in cloud cover at the planetary terminators, which is our observing region. So project 1, the quasi-biennial oscillation is a fluctuation of wind and atmospheric temperature in the stratosphere on Earth. And the GIF that you're seeing, this is a kind of representation of what that means. So the colors represent wind flow direction, and these bands represent jet streams, which are high up in the atmosphere. So the red is an eastward flowing jet, the blue is a westward flowing jet, and you can see that they form this kind of pattern of stacked jets, which are flowing in opposite direction, and that pattern propagates downwards over time. And the result of that is that if you look at any particular height in the atmosphere, like at 35 kilometers, say, it looks like the wind changes direction at that height periodically. And on Earth, the periodicity is 26 to 28 months. So a little bit more than 2 years. And one interesting aspect of this is that this is not a phenomenon which is specific to Earth, but it's also been observed on Jupiter and Saturn, and it can also be reproduced in the lab in a kind of rotating annulus experiment. So you have like a kind of rotating ring of water, and if you create some waves at the bottom, the water will form a current which will change direction periodically. So this is a kind of very fundamental physical phenomena in atmospheric flows and fluid flows, and it's not specific to Earth-like planets. And why does it happen? How does it work? So this oscillation of the wind speeds is driven by the absorption of gravity waves within the background flow of the fluid. And a gravity wave is an internal wave inside the fluid, which is generated by any kind of perturbation in the vertical direction. So by, for example, convection, or I mean, that's most of the waves that we think are involved in phenomenon are convectively generated. These waves propagate upwards and also in both direction, and they get absorbed at different levels of the atmosphere. They deposit their momentum, and that causes this pattern of jets which flow in different directions. And I'm just going to run this little video, which is made by Professor Jeff Vallis at University of Exeter, and which gives a kind of 1D simulation of the pure mathematics of this phenomenon, where it looks like you see this oscillation happening, positive and negative, and it is increasing in amplitude as it goes further down in height and over time. And so this is something that we've observed in our simulations. This data is from a simulation of Proxima Centauri b. It's just kind of our standard control simulation of this planet. So it uses the orbital and kind of radius and mass parameters that have been observed for Proxima Centauri b, which have been input into the model. And what you're seeing here is these contour lines show the zonal wind. So that's the wind in the x direction. And the solid lines are a positive flowing wind, or eastward wind. The dashed lines are a negative flowing wind. And the colors that are overlaid on that are the acceleration that's caused by the gravity waves. So in order to generate the contour fill here, we filtered out the gravity waves so that we could look at the acceleration caused only by these waves and not by anything else happening in the atmosphere. And then we compared that with how the wind was actually changing. And we see that they align quite well. So you have an area of negative flow and negative acceleration, and positive flow and positive acceleration, and the same below it. So we think this supports our reasoning that the oscillation that we see in our simulation, it kind of works the same way and has the same physics as the QBO on Earth. But there are also differences between what we see in our simulations and what's happening on Earth. So on Earth, this is a pretty symmetric phenomenon, kind of around the equator, around the x-axis. But in our simulation, we see these major asymmetries happening, which are related to the asymmetry of the atmosphere because of its tidally locked state. So in this plot, what the colors are, again, the acceleration caused by gravity waves, the same as in the last slide. And this plot is a slice along the equator. We're looking at the hot spot is right here at 0, and then we have height on the y-axis, and the contour lines are just the average kind of wind. And what you can see here is that the wind speeds are high over here, and then they kind of decrease. So the jet is slowing down in this area of the planet. And in the area where it's slowing down, there's an area where a lot of gravity waves are being absorbed. And the same down here to the west of the substellar point, which is an area where there's a lot of convection. And we also showed in our study that these areas are places where gravity waves are being generated. So they're kind of like highly unstable areas which are generating these waves and also reabsorbing them. And that has an effect on the local dynamics, which is very interesting to us because this area right here is one of the terminator regions, and that's the region that we observe when we're looking at it with a telescope. So this slide is kind of just a graphical summary of the various fluid dynamics happening in this phenomena. So we have stellar radiation coming in from the top here, and then the day side is lighter and the night side is darker. The spirals represent our big vortices of rotating air, or Rossby waves, or planetary scale wave. And the arrows represent the jet streams. So we have these kind of layers of jet streams. The red is eastward flowing, and the blue is westward flowing. And the size of the arrow corresponds to the speed of the wind. So you can see that the wind has asymmetrical speed around the planet. It's a lot faster on the night side, and particularly on this quadrant of the night side. And it's lowest here, kind of on the day side, to the east of the substellar point. And the two stars represent our sources of gravity waves, so where we think most of the energy is being generated, that drives the oscillation. So a very interesting outcome of this is that the oscillation does not, so the winds don't change direction everywhere at the same time. So this is different from Earth. We kind of think that in the QBO on Earth, the jet streams, they change direction everywhere at the same time around the equator, and we don't see that in our simulation. So these plots show, again, a slice of the equator, and this time we're centered on the cold spot, or on the antistellar spot on the night side, and we have time on the y-axis. So you're seeing a progression of how the wind speeds change over time. And in this one, you can see they start out red, which means they're flowing eastward, and then they start to change around here at the western terminator. And they're kind of unstable for a bit, so they go back and forth for a bit, and then they eventually settle into being westward flowing. But the westward phase is a lot stronger on the day side, and it barely changes direction at all on the night side. So the night side kind of resists having this physical process happening to it. And the other plot on the right shows the same kind of thing, so the same slice of the equator and the same time, but it just shows a switch in the other direction. So in this case, you're starting out with the westward phase, and then you change direction to the eastward. And again, this happens kind of first in this area between 90 west and 150 west. So around the western terminator. So just some straightforward representations of what these oscillations look like. The one on the left is the oscillation in the zonal wind speed. And you can see here, so that if you look at, for example, 50 kilometers in the atmosphere, and then you're looking at a time series in the x-axis, you start out with red and then blue and red and blue. So that's the wind changing direction from eastward to west. And the other plot shows a temperature oscillation, which is associated with this phenomena. And in this case, the time is on the y-axis. And this is, again, a slice of the equatorial temperature. And you can see that this starts out in kind of a cold phase where it's blue, and then it heats up, and then it cools down, and then it heats up, and so on. And this has the same periodicity as the wind speed direction. And probably the most interesting outcome of comparing this to the Earth oscillation is that the magnitude is much, much bigger. So the wind speeds are a lot higher. I mean, they're higher in general on tidally locked planets, but the sort of amplitude, the peak-to-peak amplitude is much higher. It's like almost 200 meters per second compared to much smaller for Earth. And even more interesting is that the associated temperature oscillation also has a really big amplitude, where on Earth the sort of peak-to-peak temperature difference is 4 Kelvin. In our simulation, it's 60 Kelvin, which is probably like a variation of 25% in the atmospheric temperature. So our models don't have a lot of atmospheric chemistry. It's basically a nitrogen atmosphere, but we do have water vapor, and the water vapor also undergoes an oscillation. And on Earth, which has, of course, much more interesting atmospheric chemistry than our model, the trace species in the stratosphere also fluctuate up and down in tandem with the wind and temperature oscillation. And we can see that also here in our water vapor abundance. This is the abundance at the western terminator in the stratosphere, fairly high up. And you can see that there's kind of a periodic regular increase and decrease. And what we did to see if this could actually have an impact on observations, whether it could actually help us observe things if we're observing at the maximum, or if it would be detectable if we were re-observing this planet in the long term, is we generated a simulated transit spectrum for the maximum and also for the minimum of this time series, and then we subtracted those two, and that's what's shown on the right-hand side here. And as you can see, this is a very small difference. The peaks that are pointed out here are water vapor absorption peaks, but the difference is only on the order of sort of 5 to 10%. And in this case, that's partially because we are simulating a planet which isn't very easy to observe. So the planet-to-star ratio for proximum star B is not really very favorable for transit spectroscopy, and it's also not transiting. So this is kind of like a hypothetical order of magnitude for this type of planet. And it's probably too small to be detected for an Earth-like planet, but because we know that this kind of oscillation also happens in gas giants, it would be a really good idea to repeat these studies with a hot Jupiter model and see if we can generate this type of oscillation and do the simulated observations and see if it might be observable for more observable planets. And that's not completely pie in the sky, so there's been some work looking at actual data to see if we can detect variability on these better observation targets. So this is from a paper that came out earlier this year, which created a time series of wind speed observations for the ultra-hot Jupiter Kelt 9b, which is shown in their plot here. And it's the solid dots, which are the data from Kelt 9b, and the time axis is the x-axis here. So you can see in this paper they make the argument that based on their calculations, the zonal jet on this planet is speeding up and slowing down, and that's detectable. Okay, so much for project 1. I'm going to move on to talking about the second variability project, which relates to clouds and how they impact transit spectroscopy. So if you've done any transit spectroscopy or observations, you You probably don't like clouds very much because they flatten your spectrum. And this is an example of that. So this is a plot from this excellent and well-known paper presenting the transmission spectrum for a Neptune mass planet. And the red here is what we would like to see when we do a transit spectrum, where we have these nice peaks at various wavelengths that we can match up with atmospheric species. And the black dots are kind of what we actually see when there are clouds, because the clouds scatter light in every direction and they kind of flatten out the spectrum. And unfortunately, that makes it difficult to impossible to tell not only what atmospheric chemistry there is, but also even whether the planet has an atmosphere or whether it's just kind of an airless world or just has a very heavy atmosphere. And that's a problem for detecting habitable planets, because any planet that has liquid water is probably going to have water clouds, and that means they will scatter the light and make it even more difficult for us to detect water vapor features. However, our simulations show that the cloud cover is not constant on Earth-like planets, especially tidally locked Earth-like planets. And there's, in fact, quite a lot of variability in the terminator regions. And we did a study to see if this could help us get better observations. So if we could potentially observe a planet on a day when there's not as much cloud, then we might be able to get a better transit spectrum. So these are some animations of data from our simulations of Proxima Centauri b. This is lower down in the atmosphere, and it shows the mass fraction of liquid cloud, which is kind of concentrated in a ring here. The clouds tend to form just in areas where the atmospheric temperature is appropriate for condensation, which is around this area in this particular model, but that varies quite a bit between simulations. And the other GIF is much higher in the atmosphere, and it shows the ice cloud, which there's generally a lot more of in this model, as it's a relatively cool planet. And you can see that this is varying quite a bit, and it also tends to be flowing eastward, and that's because of this big jet, which I mentioned on previous slides, which is carrying the clouds eastward toward the eastern terminator. So we wanted to know whether we could exploit this cloud variability in order to observe planets on clear days. And to do that, we ran 5 simulations with different amounts of cloud cover and different atmospheric dynamics. So we ran a control simulation of our Proxima Centauri b model, which uses the canonical data for this planet, and a control simulation of our Trappist 1e model, which also uses the canonical observational data for the planet. And then we did what we call the warm simulations of each of these. And what we did for that is change the orbital distance so that the planet is close in, quite right at the edge of the habitable zone. And we did this because we thought we might have a bigger effect of cloud variability on a close-in planet, and also because we have an observational bias that we're more likely to detect close-in planets. So we want to know if this effect is more useful for these types of planets. And finally, we ran a dry atmosphere Trappist model in order to study the physics that causes this variability. So what we found is that the variation in cloud cover at the terminators is not random, so it has periodicity, which you can see quite clearly in these plots. These are time series that show the average mass of the cloud at the terminators in our control model of Proxima Centauri b, and also our close-in model, the warm Proxima Centauri b. So in this one, the ice cloud and liquid cloud, which are the blue and red, are roughly at parity, whereas in this one, it's mostly ice cloud forming this simulation. But they both have a similar kind of periodicity, where you can see these roughly 4 peaks in 600 days. So why does this happen? We figured out pretty quickly that it's because the big vortices in the circulation, which we call Rossby waves or planetary scale waves, which are known to form in simulations of tidally locked planets. These are not stationary, but they actually move back and forth over time. They've previously been reported in most literature about these kind of simulations as stationary Rossby waves, but they're not. They're definitely not. So you can see in a time series or a GIF that they travel sometimes almost a full hemisphere or a quarter of a hemisphere back and forth. And the reason they affect the cloud cover is because when these vortices are close to the substellar region where there's a lot of cloud, they advect cloud over the terminators, making it cloudy. And when they are far away from the substellar region, then they don't overlap, and you end up with a clear day at the terminators. So first we wanted to understand why these waves are moving back and forth, why they have this oscillation in their location. And to do that, we compared our simulations of Trappist 1e with a moist atmosphere and with a dry atmosphere. And what these plots show is just the wind flow. at different stages in the oscillation. So this is in the moist atmosphere, you have a vortex here, and then 10 days later it's moved eastward, and then 10 days later again it's moved to its original location. So you can see these waves are moving back and forth on a time scale of about 20 days in this simulation. And in the dry atmosphere, it looks quite different. So first of all, the rotation, the wind speeds are much lower. The arrows have the same scale in these two plots. And secondly, you don't have an oscillation at all. So the wave just travels westward around the planet. It doesn't move back and forth at all. So this is purely a moist phenomena, as far as we can tell. And so why does that happen? We use the basic theory of Rossby waves to explain why this Rossby wave is moving back and forth. So this is a formula which describes the phase speed of these waves. It's just from basic atmospheric dynamics textbook. The CP is the phase speed of your wave, and it depends on the zonal wind, the wind in the x direction, the Coriolis factor, so the planetary rotation rate, and then the size of the wave. So K and L are the wave numbers in the x and y directions. And we calculated this phase speed for our two different simulations, our moist and dry simulations, to see how it developed over time. And in this time series of the phase speed in the moist atmosphere, you can see quite clearly that the velocity, it moves between positive and negative on kind of the same time scale, 5 times in 100 days, as we observe in our other data. And in the dry atmosphere, you can see that the phase speed remains negative, which means westward. So that explains why this wave is only going westward in the dry simulation. And why is that happening? So we've now pushed back our y to earlier on in the chain of logic. And we think the reason is that there's a kind of intrinsic feedback between the cloud cover in the simulation and the atmospheric temperature and the atmospheric dynamics, so the big Rossby wave. So this again is a comparison of the moist and the dry Trappist-1 atmospheres. This is the absolute temperature on the day side, and you can see that there's a periodic heating here 5 times in this period, whereas that doesn't happen in the dry atmosphere. And this is the vertical wind, which you can see is oscillating between kind of positive and negative on the same time scale in the moist atmosphere, but not in the dry atmosphere. So that means that the air is rising and subsiding in turn. And the way this all comes together is we think there's this kind of self-synchronizing feedback loop where the cloud cover drops on the day side, then the atmosphere heats up because you no longer have cloud albedo, or your cloud albedo has been reduced. There's an increase in heating in the lower atmosphere, and this increases the power of the longest wavelength planetary wave, so the biggest of our kind of rotational Rossby waves. This step is called the Matsuno Gill response in atmospheric fluid dynamics. It's been sort of described in tropical fluid dynamics, where if you have a periodic heating, the atmosphere responds by forming this kind of wave number 1 wave, and that should be proportional to the amount of the heating. And finally, once that wave has been increased, that affects the transport of clouds to the eastern terminator. So to try to correlate these things and support our feedback loop, what we have here is a correlated time series. The black line is the surface temperature in watts per meter squared, which you see goes up and down 5 times per 100 days, so on a 20-day cycle. And then the red shows the power spectral density of the largest wave, and you can see that after the temperature goes up, the wave power then increases, so it follows the increase in heating. And then we also plotted what's described as the wave sum in the plot, and that is the sum of the power of some other large Rossby waves, which these all have different phase speeds. And the reason we showed this is because we wanted to see if all the waves were being affected equally, or if maybe they were transferring energy between each other. But what it mainly looks like is that the biggest wave receives kind of the biggest boost from heating in this pattern called the Matsuno-Gill response. And then when the surface heating goes down again, the gap is not as big between this wave and the other waves. And in comparison, in the dry atmosphere, you can see that there's no correlation here between variation in the surface heating, which is very small in any case because there's no cloud albedo affecting it. There's just like a constant heating. And yeah, so there's no evidence of this kind of cycle happening on the dry Trappist 1E. But that's only half the question. So we think we understand why these waves are moving back and forth, but in order to actually have an impact on observations and maybe clear up the terminator for us, they need to be, the waves need to be in the right position to interact with the cloud bubble. And this is the same slide I showed earlier, but I'll actually explain what the plots are now. So these are just cross sections of the cloud cover. So one of them is through the equator, and then the other one is kind of through the prime meridian on the day side. And so you can see that depending on the atmospheric temperature, your cloud bubble can be higher up, your cloud deck can be higher up, it can be more extensive. It can extend, this one extends kind of between 60 south and 60 north. This one not, this one's a lot less. The cloud deck in the warm Trappist 1E, which is very close in, is very high. And this is kind of like the pre-existing state of the cloud cover, which the wave then interacts with. So to put this all together and actually simulate some observations, we took the data from around the planetary terminator. We took two absorption features. We have the 1.4 micrometer water feature and 2.7 micrometer CO2 feature. So we have fixed CO2 in the atmosphere. It doesn't like condense or anything, but it's just kind of there, and you can simulate it in your observations. And we've now made a time series of the transit depth to see how much this would actually change based on the changes in cloud cover and changes in abundance in the case of the H2O, but not in the case of the CO2. And you can see that there's some variation, but it's not really that much for this simulation, which is for Proxima Centauri b, so our control model of Proxima Centauri b. And just like with the Project 1, that's because this is not a very good planet to simulate observations for. It's not really an observable planet. It doesn't have the good kind of star-planet ratio to observe, but at least we can show that there is variation in both of these things. So we repeated this for our other simulations for Trappist 1E, and so Trappist 1E is a more observable planet because it's bigger compared to the star, and we think that, for example, the James Webb Telescope might be able to get some decent data from this planet. However, in our simulations, again, the differences are not really big enough to be observable, and in particular, the peaks are not really big enough to be observable. So, like, ideally, what we would want is for the peak to be big enough for JWST to observe. And the reason for that in this simulation is because the sort of big waves, the vortices that move the cloud back and forth, they actually form very high up at the poles, and they don't overlap with the cloud bubble, so they have no effect on the cloud cover. So the kind of the geometry of the atmosphere is wrong. And then we ran this again with our close-in, our warm Trappist 1E simulation, where the clouds form over a much bigger part of the disk. And so even though the waves are not so close to the substellar point, we think they should still interact with the clouds. And the problem with these is that the transit depths are really small, and that's because the cloud deck is so high, because this is a close-in planet and it's warmer. So in none of our simulations does this cloud variability actually help us observe the planet and its atmospheric chemistry. And that's probably broadly true. It seems like the conditions would have to be kind of just right to allow for the periodic cloud cover variations to open up observing windows. That would actually help us. So it's probably not going to help us much. So I've come to the end of my talk, but I've just got a few takeaways. That essentially the tidally locked planets should have intrinsic variability, even though they have this constant radiation pattern, and that's because of the just inherent atmospheric dynamics of this orbital configuration. Many kind of planets could support a stratospheric oscillation, which is similar to the Earth's quasi-biennial oscillation or semi-annual oscillation. And those oscillations may be big enough to be detectable, and they can also happen on all kinds of planets. And finally, the cloud cover variability, which we see in our simulation, is probably not going to help us get spectra for Earth-like planets, except in very lucky circumstances. So that's it for my presentations, but if you have questions, I'll be happy to answer them.
Okay, are there any questions or feedback or comments? Yes, please.
Yes. Thank you for this very interesting talk. I was curious, because as you said, we don't probably have that detailed observation already of the two planets. Which assumption do you have to make for the atmospheres?
You mean like the atmospheric chemistry, or?
Or also the property, like how thick the atmosphere is, and the
So we
composition.
mostly start with Earth. So we have like a similar scale height as Earth. This is a 3D global climate model based on Earth, and it's more or less been configured to run in the tidally locked configuration. Then we change things like the radius and the distance from the star, and then we use the stellar spectrum that's from the actual star. So Proxima Centauri and Trappist 1 in each case. But aside from that, it's very similar to Earth. They have nitrogen atmospheres with water vapor, and that's pretty much all. So it's quite idealized. And yeah, we don't really have a justification to, of course, we can run it with other things. We have some CO2, which has a kind of Earth-like abundance, like 380 ppm or something. Not that we're at 380 ppm anymore, but before global warming we were. But yeah, we basically start with those Earth-like assumptions and then try to like do a study where we vary one thing at a time.
Thank you.
Thank you. Yes.
Thank you for a very nice talk. Perhaps you said it already, in which case I apologize, but you've evaluated the effect of irradiation and heating on one side of the planet. Have you considered what might happen if you have tidal deformation of the atmosphere?
I'm not sure our models can simulate that, something like that. I don't think so, but it's probably, you'd probably have to ask the research software engineer. So, like, yeah.
Okay. Thank you.
Yes. So in the end, you showed very nice results for the transit depth and how it may or may not be applicable. Do you also know, is there any impact on the reflected spectra? So if you do phase curves observation, for example, clouds can have quite a reflective property. Do you know if the variability there has an impact or not?
No, I don't. So we haven't simulated those, and we also haven't simulated, like doing something like thermal emission spectra for the hotter planets would also be useful, but we haven't done those. We've only done the transit spectroscopy. But yeah, that's a good future work, yeah.
Any more questions?
Yeah, to tag along a little bit on the Sven's question on the phase curves. For example, in one of the GIFs you showed in the beginning, you could, I think, see some variation of the hotspot shift left or right. Maybe this could be something that you would be able to see in phase curves. Or actually, you also explained it in the moist versus dry plots that you sometimes see this zonal shift of the vortices.
Yeah, I think the hotspot shift is something we see for the hot Jupiters, but I don't think we really see it for these planets, which are comparatively much colder. So this is showing the wind, just the wind flow. I don't think we see a real shift in the actual like surface temperature hotspot for these planets.
Okay, thanks.
Yeah, but if you had an oscillation like this needs a water cycle, so I guess you wouldn't have that on a hot Jupiter. But maybe, for example, the other oscillation, the one in Project 1, if the jet kind of that's moving the hotspot is shifting direction, then maybe you could observe something like that from a phase curve.
Yeah. All right. Nice.
Thanks for a very nice talk, Maureen. I had a question about the self-synchronizing mechanism that you showed. So could you go back to the mechanism?
This one or the one before?
Yes, this one.
Okay.
So after step 2, if you have the increase in heating in the lower atmosphere, have you looked at what that affects, how that would affect convection, and then how that would go back to the drop in your substellar cloud cover?
So it would be nice if I could make this a completely closed feedback loop and say the Rossby wave gets increased and then that causes the drop in cloud cover. But actually a lot of things affect the cloud cover. So the convection change, there will be a change in convection and that will affect the cloud also. And also any change in the kind of tropospheric zonal jet will affect the cloud cover. So various things can cause the initial drop in cloud cover and cause that to go up and down. And then I think that the dynamic response, the Rossby wave response, is kind of a second step. And it contributes to the cloud cover drop, but it's not solely responsible for it.
Okay,
So,
thank you.
Yeah.
And if you go to the wave phase velocity definition,
this one.
Which of the factors is driving the changes most?
I think the zonal wind has a big effect. So the Coriolis effect also, because the Proxima Centauri b has a rotation period of 11 days and Trappist 1 of 6 days, so that has an impact. But I think actually the zonal jet speed probably has the biggest impact, which is a bit awkward because we don't really have a good way to connect the zonal jet speed at various latitudes or at the equator to the rotation period or other kind of aspects of the simulations.
Thank you.
Any other questions?
Yes. I was curious, since you're looking at terrestrial planets, and especially you talked a lot about the difference between moist and dry planet, do you make any assumption on the surface? For example, do you consider large bodies of water, or don't you make any assumptions on that?
So we have the same surface for all of our simulations, which is just a slab ocean, which has a certain heat capacity, and then it can evaporate. But it doesn't, we don't have any like orography, and we haven't done any experiments with things like percentage land cover, which would affect the heating and kind of affect the formation of the clouds probably, and we also don't have an active ocean with heat transport or anything like that. It's quite simple there at the surface.
Would you think that has a large impact on the variability, or do you think that?
I think the ocean circulation could have a large impact on a lot of things, and we're mostly not simulating that because it's really hard, and also because it would be very dependent on the continents, if there are any. We have no idea what kind of continents there would be. So I'm not sure. I think there have been some studies where people put like a continent and then they like change the size of it so that a certain proportion of the surface was land and a certain proportion was water. And that does have a bit of an effect. It can weaken aspects of the circulation. I don't quite remember what the outcome of the study was, but it might. I think nobody's really looked at variability very much before, so I don't know exactly how much it will impact these things. Probably the tropospheric more than the stratospheric, I would think.
Thank you.
Okay, then I'll reserve the last one for myself. So the first phenomenon that you spoke about, even if we had an instrument that could really detect such small changes, would it not be dominated by stellar activity on the same time scale, which is magnitudes larger in variability amplitude?
Not having worked with data reduction pipelines myself, I don't know how good they are at filtering that out. So I think somebody who's an observationalist will have to answer that. But I mean, I think for planets, Earth-like planets, this kind of oscillation is too small to detect. So what we would hope is that for larger planets like this one, you could detect something, or that you could explain variable observations with some kind of physical explanation that we can simulate.
Are you able to predict the period from the stellar orbit and the the orbit and the planetary radius?
We think it's not related to orbital factors like that. So the period in our simulations for Proxima Centauri b is about 6 months, whereas on Earth it's 26 to 28 months for that same oscillation. And that's probably related to the wave momentum that's being generated, so just how much energy the waves have and how much they're being generated and how much they deposit. And I think that's probably, so in Earth studies, it's very difficult to get a consistent period when simulating this oscillation.
Right.
It's been one of the most difficult things to do, and different models generate different periods. So that's probably the least robust part, like the actual period length.
Right. So we also don't know in which part of the Fourier spectrum to look actually for the phenomenon. It can be any period, basically.
Yeah.
Okay.
Exactly.
Okay. Well, if there are no further questions, let's thank Maureen again. Thank you very much.
Thank you.
She'll be around for 1 or 2 more hours, I guess. So if you want to ask more, you can find her.